Yesterday we left off on number 7. Today we are on number 8 of the Unit 7 Kinetics AP Chem review worksheet. Number 8 says hydrogen peroxide decays into water and oxygen in a first order process. So of course I circled first order because that's going to tell me some things I need. At 20 degrees Celsius, okay, and there's our reaction. The differential rate law is equal to rate equals 1.77 times 10 to the negative fifth times the concentration of H2O2, where K is in the unit of seconds to the minus 1. What's the half-life? Okay, and so what is the formula we need to calculate half-life for a first order reaction? That's the one we're familiar with, right? And so we have T sub 1/2 equals 0.693 over our K. And so my K is right here in that differential rate law. And so we have T sub 1/2 equals 0.693 over that K value. All right, let me put the unit on that K really quick. Oh, and that's why. Okay, so they wanted in hours. Okay, so once I got that value, I went ahead and did 0.693 divided by my K, and I got a T sub 1/2 equal to 3.92 times 10 to the 4th seconds, but they want hours. Okay, so I went ahead and set up my dimensional analysis, changing this to hours. So we have 1 minute, 60 seconds, and then we have 1 hour, 60 minutes. And so I get a final answer of T sub 1/2. The half-life is 10.9 hours. Okay, number 9, we're studying the reaction to A yields 3B, and we make a plot of the natural log of concentration of A versus time as the reaction proceeds. The plot turns out to be linear. Okay, so what does that tell me? Since I plotted natural log of concentration of A versus time, and I got a linear graph, what does that tell me? What kind of order is this? It's first order. That's right. So I wrote that down first. And so we know the slope, bless you, the slope is calculated of that line. It's negative 0.25 inverse seconds. What's the differential rate law for this reaction? So since it's first order, let's scroll up here, we just have a rate equal to our K, which is the absolute value of that slope, isn't it? So 0.25 seconds to the minus 1. Go ahead.
Negative or?
We want absolute value.
Oh, okay.
Mm-hmm. Times the concentration of A. And there's no exponent there with A because it's first order. Okay, so that's it. That's my answer from that one. Okay, on number 10, we're studying the reaction of A yields to B, and a plot of 1 over concentration of A versus time is developed as the reaction proceeds. This plot shows linear with a slope of 1.87 liters per meter second. What is the rate law expression for this reaction? Okay, so since we had 1 over concentration of A versus time show us a linear graph, what kind of reaction or what order, would this be? Second. When we plot data dealing with concentration versus time, there's 3 graphs we make. The first one would be concentration of A over time. Second one would be the natural log of concentration A over time. And then this would be the third type of graph. Whichever one shows us the straight line, that tells us what order it is. Okay, so if the natural log times the concentration of A shows the straight line, it's first order. If the 1 over concentration of A shows the straight line, it's second. And if it is the just concentration of A versus time, it's 0 order. So that was just something we had to memorize. Good question. The plot is linear. Okay. Oh, we already did that. So we're doing rate law expression. Okay, and we have A to work with here. So we have rate is K, which is going to be the absolute value of our slope for that straight line. Times the concentration of A. And since it's second order, we need the exponent 2 on that concentration. That's my answer there. Okay, on the next one, the oxidation of iodine ions by arsenic acid in acetic aqueous solution occurs according to the stoichiometry shown above. The experimental rate law of the reaction is as follows. What's the order of the reaction with respect to iodine? Okay, so what did you have on that one? In respect to iodine. This is an example if they give you way too much information, you really don't need all that. Where could you look? Say it again? I didn't. I looked right here for an exponent. And so there's an understood 1 there, isn't there? Okay, so in respect to iodine, it's just first order.
I'm sorry.
That's okay. There's not an exponent over here with I in our rate law. And so it's first order in respect to I. It'd be first order in respect to any of those substances. Mm-hmm. If there was a 2 there, we'd say second order. What would you say if they wanted the overall rate order? 3. Yeah, it'd be 1 plus 1 plus 1. Good. Okay, on 12, according to the rate law and the reaction that we just saw, an increase in the concentration of hydronium ions has what effect on this reaction? Let's look back at that. So we're increasing those hydronium ions. Will the rate of reaction increase? Well, let's hang on to that one. Will the rate of reaction decrease? That one definitely makes no sense, right? Okay, will the value of the equilibrium constant increase or decrease? Will K change at all? Now, what's the only thing that changes K for this reaction? Temperature change. That's right. So we can eliminate C and D. And so we know that the rate's going to change. Oh, well, it says neither the rate nor the value change. Well, we know one of them is going to have to. So the rate should be our answer there. Remember, if I'm increasing this value, it's going to make my rate increase also. So if we think about it mathematically, if we're increasing this value, it's also going to increase this value here. On 13, in a reaction in which rate equals K times concentration of X times the concentration of Y squared, what would be the effect on the reaction of doubling both the concentration of reactant X and the concentration of reactant Y? Look at X first, and what order is X? It's in first, and so what effect on rate would X have just alone? It's going to double it, right? Okay, so if we're thinking about just X, it's going to double the rate. And now we have Y, which is second order, so how is Y going to affect the rate? It's going to quadruple. Okay, so what's my answer on this one? It's going to increase by a factor of 8. We just do our 2 times 4 and get 8 on that. Yeah. 14, for the reaction which has the rate law, rate equals K times concentration of X, a plot of which of the following would be a straight line? Okay, so for first order. Say it again. The natural log of X versus time would give us a straight line because it's first order. Okay, let's look at this reaction mechanism problem. Well, not quite yet. Okay, they're showing us some elementary steps. Okay, it says the proposed steps for a catalyzed reaction between Ce4 plus and Ti plus are represented above. The products of the overall catalyzed reaction are. Okay, so how are we gonna tackle that? What are we gonna have to do to those steps to see our overall? We're gonna have to start canceling things out. Yeah, that appear on both sides for sure. So on that, I have canceled out my Mn2 plus on both sides. I've canceled out my Mn3 plus here and here. I've canceled out my Mn4 plus here and here. I believe that's all that is canceled. And then I went ahead and just wrote my overall reaction off to the side. We have 2 Ce4 plus. And for my products, I'm left with Ti3 plus and 2 Ce3 plus. Okay, so that matches up with answer C. Bless you.
Sorry, you went fast.
No, it's fine. Oh. I just took all of that and combined it into a reaction. Whatever didn't cancel out. No, that's a good question. Okay, on 16, relatively slow rates of chemical reactions are associated with which of the following? Slow rates of reaction. All right, would a presence of a catalyst slow the rate? No, it's going to increase the rate. Will a high temperature slow the rate? No. Will a high concentration of reactant slow the rate? No. Will low activation energy slow the rate? No. So we have strong bonds and reactant molecules. Okay, so process of elimination there, or it would take more energy to break those bonds. So it might take a little more time to do, be a slower rate of reaction. Okay, 17. The following data were obtained from a study of the decomposition of a sample of HI on the surface of a gold wire. After graphical analysis, the graph of the concentration of HI versus time was found to have a straight line, and there's your slope. So since the concentration of I versus time gave us that straight line, what order of reaction is this? 0. Good. We are 0 order here. Okay, so for part A, of course, look for your time there. We're in seconds. And of course, we have concentration, so moles per liter there for our units. So determine the rate law for a 0 order reaction. Remember, on the 0 order, our rate is just going to be equal to our K, because anything raised to the 0 power, right, would drop out because it's just equal to 1. Let me write that over to the side. If we had this, which is 0 order, that would drop out as 1. So it's just rate equals K on that. Okay, to determine the rate constant, we would just take the slope of that straight line and find the absolute value. Okay, so K is equal to absolute value negative 0.005546. And so our K is equal to 0.005546. And now units for K, since we are 0 order, we would be moles over liter. So mole, liter to the -1, and we still have to put our seconds to the -1 on the end. Okay, give the integrated rate law. Since this is 0 order, my integrated rate law would be concentration of HI minus concentration of initial concentration of HI equals negative KT. And I was looking at your resource for the AP test, and the integrated rate laws are listed, but they don't say what order of reaction goes with which integrated rate law. And so at least they give you this. You would just have to know when to use it. You already have it. It's in that that little packet with the periodic table, the AP periodic table, and the resources in that with the equations and constants and everything. It's there. Yeah, I was looking at that yesterday. Okay, so if we were calculating concentration of HI at 6.0 seconds, now we have our elapsed time. And because of that, I need the integrated rate law. And so we are solving for the concentration of HI at this time. And to get our initial, remember, we just have to go back up to the chart. And so our initial concentration was 5.46 molar. Equals our negative K. I'm going to leave off the unit there, times time, which is 600. Let me erase that. 600 seconds. So when I enter that on my calculator, I get a concentration of HI equal to 2.13 molar. Set a 2 and I wrote a 1. Okay. Moving right along, law number 18. Okay, there's our reaction. It says when the concentration of substance B in the reaction above is doubled. Okay, so we're doubling concentration of B. All other factors being held constant. Okay, it is found that the rate of the reaction remains unchanged. So how could we explain that? Read through those answers. What do you think on that one? A says the order of the reaction with respect to substance B is 1. Does that make sense? No. If it was first order, then we know it would double. It would double the rate. The substance B is not involved in any of the steps in the mechanism of the reaction. No. It would have to be. C, substance B is not involved in the rate determining step of the mechanism, but is involved in subsequent steps. That would have to be our answer there. Okay. D says substance B is probably a catalyst. So its effect on the rate of the reaction does not depend on concentration. The last part of that makes that not true. And then E, the reactant with the smallest coefficient in the balanced equation generally has little or no effect on the, no. And that's just kind of like for our answer on that one. Okay. On 19, we have a proposed mechanism for the decomposition of ozone. Okay, and so there's our overall reaction. Here are our elementary steps. And so they want us to derive from that the rate law equation for the net reaction. Where do I want to start? It's kind of like the first thing I need to do on this. Cross out. Yeah. I'm going to cross things out. Okay, so O's are 0, or O is on both sides there. I'm going to cross that out. Okay, we're left with our two O3s, our O2, and our two O2s, which combine to get the overall reaction. So that looks good. And now what I want to do is I want to use the slow step and determine my rate law for the slow step, because it's going to determine the overall, right? If you're running a race with little kids, they're going to determine your rate, right? Your speed. Mm-hmm. We saw that at the park this weekend. We took my little ones. Okay, so rate equals, okay, I'm going to have the concentration of oxygen times concentration of O3 Okay, so that's based on the molecularity. And so now, is that okay? Can I go ahead and report that as the rate law? I can't. Why can't I? Which one of those do I need to get rid of? Yeah, I have to get rid of O from that. And so I'm going to use what I know about my first elementary step. And so we can think of that as concentration of O3 equals the concentration of O2 times O. I need to substitute something in for O, so I want to get O by itself up here. Okay, so to do that, I'm going to divide by O2 on both sides. And so I get O equaling concentration of O equaling concentration of O3 over concentration of O2. And so what I'm going to do is I'm going to substitute this in for the O I don't want in my rate over here. Okay, so we'll have rate equals concentration of O3 times concentration of O3. We still have to bring this down over concentration of O2, and then we just need to combine those O3s. And so we get an overall rate equals, and we left K off. We need to add K in here. Let me do that. Don't want to forget K. So rate is equal to K, and we have O3 squared now over O2. So it kind of reminds us of Hess's law in a way. Okay, at least it does me. Okay, for the free response. Okay, again, we have some elementary steps there. It says environmental concern is the depletion of O3 in the Earth's upper atmosphere, where O3 is normally in equilibrium with O2 and O. A proposed mechanism for the depletion of O3 in the upper atmosphere is shown below. Okay, so there's our steps. It says write a balanced equation for the overall reaction. So we want to, just like we did last time, cross out anything we can. And cross that out. We can cross out our chlorine. And that looks like all that we can cross out. So we're left with O3 plus O yields. Now, since they said it's in equilibrium, we would want to draw an equilibrium arrow there, but that's our next unit, so don't worry too much about that right now. And we have two O2s. Okay, so that's my overall. Clearly identify the catalyst in the mechanism above and justify your answer. Okay, so which one is our catalyst? Is it the ClO or the Cl? Which one? Cl. How do you know? Because it shows up right here, and it is still here at the end of step 2. Okay, what's that tell you about ClO? It's an intermediate, right? Because it appears and disappears. Good. Okay, so the catalyst is chlorine. It appears, or it's added really. Let's change that. We also want to point out it remains unchanged. Because we know a catalyst is not changed during the reaction also. Clearly identify the intermediate, and so the intermediate would be our ClO. It appears as a product in step 1. and is used up during step 2. Okay. Part D, if the rate law for the overall reaction is found to be rate equals K times concentration of O3 times concentration of chlorine, determine the following. What's the overall order of reaction? 2. Yeah, so we have an understood 1, which each of those. So our overall is 2. So based on that, what would be the appropriate units for the constant K? We're thinking 1 less than 2 is kind of our trick there. So we have liter to the first, which is just liter, times mole to the negative first. And then we need our time in there. So our time was in, doesn't tell us our time. Okay, so we're going to put seconds there just because that's the most common. And I'll make sure that's clear in the test. If it's not, I'll take another look at that. Okay, the rate determining step of the reaction along with justification for your answer. Which step would we want to, okay, think, well, that's another mistake I'm seeing, y'all. They didn't label those reactions, did they? Step 1, they go ahead and put a slow next to step 1 and a fast for step 2. That should have been given to us. Okay, and so now which one is the rate determining step for the reaction? The first one, the slow one, right? So the rate determining step is step 1, the slow step. And then for our wording there, the AP really wants us to use that word molecularity. Okay, so the rate law matches the molecularity. Of this step. So I guess so if they didn't label, we could have determined that anyway. Okay, because we know an overall reaction. And so if we had written out our proposed rate reaction for step 1, it'd be rate equals K times concentration of O3, concentration of chlorine. Well, no, that wouldn't work either. No, they had to tell us. I just wanted to look at that real quick. Do you all get that written down? Okay. Let's look at the next one. Okay, AP free response. For the gas phase reaction represented above, we have the following experimental data. Okay, so for part A, what we want to do there is use the method of inspection, if we can, okay, to determine the order of reaction with respect to A and B. And so let's see if we can do that. In order to be able to use inspection, we have to see that the concentration of A was held constant for one experiment from one to another, and concentration of B was held constant from one to another. And so we see on experiments 1 and 2, I'm told that this is close enough for us to be able to use inspection, even though all the problems we've worked were exactly the same concentration. These are close enough that we can use inspection, I was told. Okay, so let's look at concentration of B. Again, I was told that we were close enough here. Let me change my color on that just because I wanted to do that in a different color. Put my arrow on the other side. Okay, so first let's determine the order of reaction with respect to reactant A. So on that, what I want to do is look at experiments 2 and 3. Okay, so we start out by saying in experiments 2 and 3. Remember, there's a template we're using to answer these because AP is very particular about how these are answered. In experiments 2 and 3, the concentration of B is held constant. While the concentration of A does what? What did it do? So we're looking here for A. What did it do? Tripled. Sorry, quadrupled. Okay. What reaction or what effect did that have on our rate over here? Okay, so that's what we want to describe next. So this caused the reaction rate to do what?
Decrease.
What's that? Not change. Not change. Because of sig figs and all, I'm told that is close enough to say no change on that. Because remember, with inspection, we're kind of doing some estimation, right? If we wanted to know exact, we could do our math on that other method we learned. This caused the rate of reaction to remain the same. Okay, and so since it stayed the same, what does that tell us about the order of reaction in respect to B? Or sorry, the order of A, sorry. Therefore, in respect to A, the order is, I heard it, 0. Is that what we said? Since there was no effect. Okay, if the rate had also quadrupled, right, we would say that it was first order in respect to A. If it was, increased by a factor of 16, then we would have said it was second order, right? So now we'll do the same thing with reactant B, and we're going to look at, we decided experiments 1 and 2 for that. Okay, so in experiments 1 and 2, the concentration of A was held constant. While the concentration of B what did it do? It quadrupled as well. Okay, so then we look at what that did to the rate. So this caused the rate of reaction to increase by a factor of 16. Remember on that, if you're not sure by how much it increased, like I'm not really good at doing that in my head, you can take the higher value of the 2, divide it by the lower value of the 2, and get that factor of increase. Okay, so and so since it was increased by a factor of 16, therefore in respect to B, we are what order? Second. Yes. Let me change that. I don't like putting we in my answer. For in respect to B. But the order is second. Yeah.
Well, for A, you said we can estimate the rate of reaction from 16.
For 1 and 2. I took the larger of the two numbers, which is the 1.08 times 10 to the negative 2. I divided it by 6.67 times 10 to the negative 4. Someone check that for me. Let me just check it real quick. I got 16 when I did that. Okay. So on part C, we are writing the rate law based on that information. And so we have rate equal to K. We know since A is zero order, it's going to drop out, right? Because anything to the 0 power is 1. So we just have to put B in our overall rate law down here, and it's squared because it's second order. Okay. Determine the value of the rate constant K. Okay, so I picked my first experiment, and I just wrote the rate of that first experiment. So I used experiment 1. I used 6.67 times 10 to the negative 4 equals K, which is what we're solving for, times concentration of B for experiment 1, so 0.034. And we need to square that because it's second order. And so when I type that on my calculator, I get a K equal to 0.58. Since it's second order, our unit, think 1 less. So we have liter times mole to the minus 1, and then we need our time, which is a second. That's my K. To calculate the initial rate of the reaction, okay, again, we know our rate law is rate equals K times concentration of B squared. Okay, and so I have my rate, which is what we're solving for, equal to, I'm going to plug in my K here. And my initial value for B is 0. Oh, sorry, no, we're doing this for experiment 4. I'm sorry, I should have read ahead. We're just filling in the blank area in our data chart on experiment 4. So we're going to use the information from experiment 4 for concentration of B. And so that would be 0.233. molar, and we squared that. And so when we enter that in our calculator, we should get 0.031. Moles, liters, seconds. Okay, another mechanism. Following mechanism has been proposed for the reaction. We have step 1 and 2. Provide 2 reasons why the mechanism is acceptable. Okay, so first we need to kind of get an overall reaction. And so we can cross out E. We can cross out B, one of our B's. And so our overall, we're left with A plus B yields C plus D. So if I write the, time's about to write up, isn't it? 3. Let me go ahead and finish this one. So if I write the rate law of the slow reaction, it would just be rate equals K. All right, you guys have a good day. We'll finish just a little bit of this tomorrow, which is barely anything, and then we'll just go ahead and take the test after that. Okay. You guys have a great rest of your day.